All right, I think we're going to go ahead and get started. While the last few folks pop in, make sure you sign in on the corner of the table and grab some lunch. But we're a little past 12, so I want to go ahead and get started, especially because we have a couple of folks on our webinar broadcast as well, so I want to get this started for them. But to everyone, thank you for coming to the September BSUG session. I'm really excited to have Ery Djunaedy from our lab present on this particular topic. He's a man that needs no introductions, but I'm going to go ahead and give some of his credentials anyway. So he works at the lab. He's a research scientist, and he has degrees in the areas of building physics and science from the following institutions. There's the Institut of Teknologi Bandung, Indonesia, the National University of Singapore, and the Technische Universiteit in Eindhoven, Netherlands, which I think is Technical University. I'm not totally sure. Okay. Excellent. And Ery also, of course, teaches quite broadly building simulation and building simulation activities, and currently actually is teaching about 22 students from the University of Idaho, both from up north in Moscow, and also some of the students down here for the graduate architecture program. I believe there are also about 3 or 4 mechanical engineering students in the midst as well. So actively teaching currently and working on multiple simulation projects here at the lab. So with that, I'll go ahead and turn it over to Ery.
Thank you, Jake. No. Minimize. Yes.
Okay.
Okay. Thank you, Jake. I hope that you're not surprised reading the title of my presentation, which is, I think, it's going to be the third of from the email circulation. The third title that we have it on there. There's the first one, there's the second one, and now there's the third. I changed it intentionally to make it more suitable for our, the umbrella event is the Building Simulation Users Group. So instead of talking into the details of the measurement and verification, I want to wrap the whole project and make it more more geared towards simulation. So as a background of this presentation, this is some of the results that we have from a project commissioned by Idaho Power, where we go to one particular building, and then we do all sorts of measurement with the intention to calibrate the energy model. So that is the initial purpose all along. So that is why I'm less interested, not less interested, but I think it's more appropriate for this session here to focus more on the calibration part instead of talking about measurement and verification and whatnot. Of course, that too is important topic, but probably for some other time. So, targeted calibration. What is the topic? I will go through what is the topic, how I come about to this topic, and then I will go to the building description, and then the energy model, and then I will talk mainly about targeted calibration. And I think this is an important topic that we've been playing in thinking at the lab to sort of to enlighten us, or to enlighten the world, to take the world out of the Middle Ages, because as we will see later, that the calibration process is more or less black magic, even for experienced energy modeler, there is no method, period. There is no method in doing calibration. So that's why this topic is important and timely, because it's about time for us to move from black magic towards more scientific-based calibration, and that's what I call as targeted calibration. I will talk more on this later, and I will focus on that. Over there, I will over here. I'm going to use the mouse to point so that the people online can see what happens. On the right side here, I have listed a lot of examples on how to use targeted calibration to use these measurements as a targeted calibration. But I will only talk about 2 of them for this presentation. All right. So initially, the topic is about savings quantification, because at the end of the day, that's what Idaho Power is interested in. Typically, they give incentives, and they want to know whether the incentives works at the operational level, not only at the design level. So that is the initial intention of the project. So we start from the EEMs, and then we go to the building, actually measure the performance, and then if there is something that is not actually working, we provide feedback to how to tune up the building, and then we compare that measurement with the predicted savings of the energy simulation. But we can, of course, talk about it from entirely separate point of view, which is simulation calibration, which is pick up the model. We start from as design energy simulation, and then measure the major components, measure the pumps, measure the heat recovery unit and whatnot, and then update the model and present it to you. But I think this has less value, so that's why I will go right in the middle of the 2 topics above. Okay, I will not present any savings quantification. Probably I will save it for later BSUGs, for another topic. And no calibrated model. I'm not going to present actual calibrated model. Okay, but I will present how we are going to do the calibration, and we will look into the pointers provided by this method. And as I've said, I will cover 2 examples. Okay. Now, a building description. The building description is 74,000 square foot, 3-story building with a basement. Municipal police and fire departments, mixed space type. There's office, there's public space, there's lab and whatnot. Of course, mixed operation too. Some of it 24/7, some of it 9 to 5 area. The building uses ground source heat pump system, and what it means is that it uses the water to air heat pumps that will extract or bring in heat, exchange heat from air to the water loop, and then from the water loop it's connected to a ground loop heat exchanger that will dump the heat down the earth. And it also has the DOS, dedicated outside air system, with energy recovery. And of course, they also install the VFD, variable frequency drive, on the water loop pump. Now, these are the important major HVAC systems equipment that is typically, they consume a lot of energy. And so that's why we are going to focus to these equipments, major equipments here. So it opens in 2012. We have the data since the beginning of 2012 and consumes about 1.5 million kilowatt hours a year and about 3,300 therms of gas. So this is the data from March 2012 until last July. Okay. On an annual basis, it's basically electricity building with only about 6% gas all year round. Okay. Fluctuating, the gas is fluctuating, of course, high in winter and low in summer. And the EUI, I have 6 months of running EUI for the last 6 months, which reduce the number reduces from 77 to 72. I think this is, of course, initial operation will have, a lot of tune-ups going on, and I think they're doing a good job in fine-tuning the operation that we see this decrease in the operation EUI, energy consumption. Moving on, the energy model. The Aqueous model, as I said, it has 3-story, 1, 2, 3 story, with a basement down below. And the ground source heat pumps in Aqueous is modeled using a package variable volume, variable temperature connected to ground source heat exchanger, and so far so good. But then the next one is the catch. Every heat pump in the building, not in the building, in the model, every heat pump in the model has its own isolation path, which means that the heat pump can say, I don't want any water flow, so that the overall water flow in the loop can be reduced, and by that the pump will also reduce the pumping capacity. That is an ideal situation, which is not the case in the building. So we will see later, it's only a handful of, probably a bit more than half of the heat pumps that have this isolation path. Okay, and the second one that is very important is that every heat pump has its own energy recovery unit, which is not the case because the building has a dedicated outside air with its own air loop, with its own single heat recovery unit up on the roof. And this will raise a number of questions. For example, how do we include the fan at the makeup air unit? Because if we model it this way, then the fan will be the fan of the heat pump. So there is that question, but we'll address it later. So these are the discrepancy that, of course, it's expected to happen, and because anyway, this is a modeling, right? It's not an exact replica of the real world, but it's a simplification. Okay. And the model came back with 65 kBTU per square foot per year, which is a bit low from 72.3, but not too bad. It's about 11% error. Okay. It's not way off. And this is the two parameters that we use for calibration: the CVRMSE and MBE. These are two types of error that we always have to report every time we do the calibration. And basically we compare the meter and the simulation on a monthly basis, and then we plug it into a formula, and we can come up with these two types of error. The first one is CVRMSE, is 14%, and the MBE of 10%. I can't quite remember what's the criteria.
15% for the CVRMSE, and the revised error is 10%.
10%. So it is considered calibrated. So not bad for an as-designed model to be so close with the meter data. Okay, so without doing anything, I can come back to Idaho Power. Hey, you don't have to do anything. It's calibrated. Yay! Right? But of course, that's not the point of doing the project. We want to dig deeper on what counts that 15%. It's right on the border of the criteria, so to say. All right. Moving on to the inverse modeling technique, which is the underlying method that I propose we use for calibration. Now, inverse modeling technique is an old Ery project. It's been around for a while, okay, but it's not used for calibration. So it is another modeling technique. It's just inverse, because traditionally when we say modeling, we will come up with building parameters. We draw the building, we plug in the thermal parameters, and then we drive it with the weather data, and then we come up with an energy use. That's how we typically do simulation. So the inverse modeling technique starts from the other way around. It doesn't start from the building parameters, but it starts from the actual consumption. So we start from the other end. For inverse modeling, we collect all the data, all the energy bills, gas, electricity, and geothermal and whatnot, added up all. And then from that, we come up with a statistical model. And with that statistical model becomes the signature of the building. That becomes the signature of the building, where from that signature we can guess the building thermal characteristics. So this is more powerful in the sense that, and meter data will never lie. It's there. It's what the client pays, what the building owner pays. Okay, it never lies. It's there. Okay, and then based on that fact, we can create a very powerful, very simple, but very powerful statistical parameters that will tell you this is how your building operates. Not only the built-in characteristics like the U values and whatnot, but also how your building actually operates. Okay, this sounds incredible, right? It's a very good tool, very powerful tool, and yet it's also so simple. Typically, inverse modeling technique is not used in conjunction with an energy model, but it's used separately to as a way to quantify savings. So this initial project the so-called the measurement and verification project that we do for Idaho Power comes from this area. We want to quantify the savings. Okay, Idaho Power has paid incentive this much for this EEM. We go to the building, we measure, and we use this method to quantify the savings. Okay, per year, this many kilowatt hours is the savings. But then, why should we stop there? Why should we stop there? We can use that energy signature to actually do the calibration of the energy model, so that the energy model that is developed in the design stage, right, can be used as a diagnostic tool. Okay. How does it look? Depends on how many parameters do you want, and this is also depends on the types of building, but typically this is how it looks. Okay. You will have the energy data on the vertical axis. This is the energy, and you plot it on the horizontal axis, not to time. So this horizontal axis is not time, but outside air temperature. So if you have January energy bill in there, for example, this point, okay, you will plot it to the monthly average of January. Very easy. You take all the outside air temperature, outside air, not inside, outside air temperature throughout January, average it. Boom. You have that, put it there, and put your energy reading right there. One at a time, 12 months. If you have 12 months, you have 12 months. If you have multiple years, you can plug it in that too. And this is actually better because then you will have a weather normalized signature. It doesn't matter which year, whether you have a cold winter, whether you have a hot summer. It doesn't really matter. You put it there, and you have the weather normalized energy signature. That is a characteristic of your building. Okay? If you have the equation, if you have the points like that, okay, you can have you can run the statistical parameters, and the statistics will draw this line, these two pieces of line, okay, and these three parameters, the EI, the T change phase, and the cooling slope, these are the signatures of this building. As long as you don't change the building, as long as you don't change the operational parameters of the building, you will have exactly that, no matter which year. Okay? You will have exactly the same. Okay? Then this becomes a powerful tool. For example, if in 1 year you will have different number. If you have different number, then you can say your building has changed, or the operation has changed. Okay? Of course, this number means something. Okay? The easiest that of course we are all familiar. This one is the balance point temperature. That temperature in the corner of this line, right there, is the balance point temperature of the building. Okay? Above which the building will need some sort of cooling. Okay? That is why this is called the cooling slope. And depending whether the slope is steeper or lower, you will have the efficiency of your cooling system. Okay? not only the efficiency of your chillers, but the whole system level efficiency of your cooling system. Okay, and this the base load here, the EI, is actually the base load of your building that does not depend on the weather. Okay. Now, what's interesting is not a single signature. What's interesting is if we have two different signatures for the same building. Of course, that's what we want if we have an energy efficiency upgrade. Okay, so that we can have one signature pre-intervention and another signature post-intervention, and then we know exactly how much savings we have. Okay, so these are a number of scenarios where you see over here, for example, on scenario B. Okay, the cooling slope becomes lower. It's less steep. Okay, it means what? It means your cooling system becomes more efficient. It's either, you can have a new chiller installed, or you have a VFD installed in your one of the major fans, for example, that will reduce overall energy consumption. But that's the effect that you expect. Okay. Another example over here. The base load is the same, the cooling slope is the same, but there is a change in the balance point temperature. Now you see, now you can start thinking there is a change in the energy signature. It means something. Okay? Now, here's the targeted calibration. Energy meter will have a signature, and the energy model will have a signature. By comparing these two, you can tell exactly, oh, my energy model needs to change this. I have to turn this dial in my energy model so that it becomes less of a black magic. Right? So that's why, you see, if we come back to this monthly energy consumption, typically we have this on a month-by-month basis, and we can say, oh, in the simulation, in the comparison, the simulation predicts lower energy consumption in summer. What can that be? We don't know. Your guess is as good as my guess. So, for me, that is not good enough. Too much magic. Okay, that's why I'm going towards this direction. And here is an example that I did for this particular building. This is the inverse modeling technique for the last 12 months from the meter. Okay, from the meter. It is not straight line and then curve, but now it's like a V. It's a signature. Okay, it's a signature. That's fine. So now we have a cooling slope here. Heating slope here. We have a cooling slope here. Okay, we still have the base load here. The base load, and we still have the balance point temperature right there. So now we have 4 parameters. Okay. Now, what are the 4 parameters? That's what it is. This is the base load over here, 373,000, and the balance point temperature is 59.2 over there. And then the heating slope is minus 4,700, and cooling slope is that. This is from the energy meter. Now, go to the simulation, we can do the same thing. But look at that. Okay, it's different. It's different. What happens here? It means it has balance point temperature. We can identify that. It has a base load. Okay. It has a cooling slope, but it barely has a cooling slope. Okay, which means what? It doesn't matter how hot the summer is. The energy model will deliver cooling for free, more or less. Okay, that's what it says. Okay, that's what it says. Now, by comparing this two parameters, okay, by comparing these two energy signature, you can see that the base load is close enough. Okay, close enough. The balance point temperature is close enough. The heating slope slightly, but a huge difference in the cooling slope. Huge difference. So now, if I need to tweak my energy model, I know where to work, which dial I need to turn. Correct? We don't have to guess anymore. I need to focus on the cooling side, for sure. And I need to identify what are the major equipments that affect the cooling energy consumption. And with that, I come back to the discussion of the isolation valve on the heat pump. This is actually the actual count of heat pumps. So there are, I don't know how many, total 67 right here. There are 67 heat pumps in the building. 14 has no valve, and with valve is about 53. In terms of capacity, that's about 65% of the total capacity has valve. Which means what? Which means that if all the heat pumps with the valve simultaneously at the same time closes, no cause for heating, no cause for cooling, I would expect that the pump circulating the water will be at 65%, or working at only 35% of the capacity. Okay, which is, I think, the lowest it can go with the VFD. Okay, which is good. Okay, we cannot go lower than that. But the problem is, does the pump actually do that? Of course, in simulation, it does exactly that. Okay, but does it actually do it in reality? And this is an example of the compressor of the heat pumps and the open and closing of the valve. Okay, you can see here, it's this particular heat pump, when it's shut off for this period of time, it doesn't coincide with the pump energy consumption. The pump, we can see there is a high average and low average here. We can see savings of about 25%, which is good for a pump this big. It's already a significant savings. But my question is, why 25%? Why not 50%? because it's supposed to reach 50% or 65% savings. If we can get 50 out of 60, that's, I think, good enough. But, you know, if we only have 25%, oh man, I mean, what's wrong? What's wrong? Okay? So, I think this is part of the reason that the energy, the meter has more energy consumption than the model. Okay? One possible answer. Okay, we can tweak that. We can tweak this. So there's pump high activity in that area. But what causes the high pump activity in this? Okay, is there a missing, isolation valve that doesn't work really? That needs to be tracked down. All right, and the next possible culprit for the discrepancy is the energy recovery unit. Okay? Of course, in the simulation, every single unit has a heat recovery unit, and it all works perfectly good all the time. Okay, and that's why I think the energy consumption becomes much lower, because it works perfect, which is not the case. So we went there and logged from April to end of June. I think it's still logging, but I haven't present the result. So this is the calculation of the efficiency of the actual efficiency, not what's on paper. This is, we measure 4 streams of air and calculate the efficiency, the actual efficiency of the time. So we measured 4 streams of air, the incoming from outside, then the outgoing from the heat recovery, and then the return and the exhaust. We measured that, and we have 2 delta T here, and you see the status. I make this up, right? But I can identify four status of operation in the for the energy recovery unit, which is not in the manual. Okay, the status 1 and status 2. Okay, it's actually in heating. 1 is in heating mode, 2 in cooling mode, and it actually cools the air or heats the air. It works the same way. When it's in heating mode, the unit actually heats the air. When it's in cooling mode, it actually cools the air. But there is a -1 status, which means it's in the heating mode, but it's cooling the air. All right? It happens. It happens. I mean, unless the logger is, messed up. But it happens. There is this -1 status. There is -2 status, which is, it should be in the cooling mode, but it heats the air. It works the opposite. And when I say it should be in the cooling mode, which means that if it should be in the cooling mode, it means that the return air is lower than the outside air. Okay? In the heating mode, the return air is higher than the outside air. Okay? This is not spelled out in the in the manual of the heat recovery system. But this will never happen in the simulation world. Okay? And we need to capture somehow how to capture this. Okay? Now, based on that status, I also calculated the efficiency of the whole system. I think the other from amongst the data, I can identify a cool week in June. Imagine that. In June, we have a cool week where, where the status is 1 all the time. That means it's heating mode, and it actually heats. The heat recovery unit heats the air. Okay? The efficiency is about 0.6. Maybe not too good. Okay? But that's what we get from this particular unit. This is only sensible. I don't count the later. Okay. It's only sensible efficiency. In the warm week, where we actually have a cooling efficiency, okay, cooling, it's more erratic in the sense that the status call can be -1 or -2. But when it works properly in status 1 or 2, it has it's quite decent efficiency. Now, what does this say? Well, of course, there is a control sequence that somehow messed up. Okay, that's what exactly this tells us. And this is another thing that we found out in going actually go to the unit. You see, when we go to the unit, of course we read it from the energy management system. So our first thought is that, oh, we need to fix the energy management system to, the control sequence have to be right. But apparently that may not be the case because, the unit may have its own controller. And the energy management system will only just read whatever the unit is actually doing. So that's another wrinkle in this. And I don't think it is anticipated by the consultant during the design who should have the controller and how the control sequence have to work. That's another lessons learned from this project. But I think we will have another presentation just for that measurement and verification part. I think that's all. That I want. Is it too fast? No, I have 10 minutes for questions if there is. That's all that I would like to present. As I said, two case example on the pointers that is actually pointed by the method that I proposed. Okay, so it's not randomly come from abracadabra and we have to turn this dial. No, but methodic steps towards a calibrated model. Questions? Ma'am.
Where did you say that you first
It's from ASHRAE. It's an ASHRAE project, American Society for Heating, Refrigeration Engineers. Blah, 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 blah. It's from originally from ASHRAE's project. So if you are ASHRAE member, you can download the report. It also still has an old statistical model that comes with the report. But you can also download a software called eTracker, which is free, that will do exactly that. What I did. And there's another pro version of the eTracker called Energy Explorer. But for that one, it's not. Marco?
Yeah, that answers one of my questions about when you're measuring the data, where do you get most of you got most of your data from control systems, not from individual thermostats and data logging? Is it difficult to log in and use the information in the different types of control systems?
That is another lessons learned from this project, is that many building owners install energy management system, but very, very rarely that they download the data and actually analyze the data. Probably this is because probably this is because a very nice graphical user interface where you can just click and it will show you an air handling unit with all the nodes actually in there. But that's just a snapshot of that particular point, which is, it's not logged, it's not recorded. The next 15 minutes, that data is gone, replaced by another data point. Nobody is logging. Well, I shouldn't say nobody is logging, but you see, from let's say 2,000 data points available in a small building, for example, from 2,000 data points, how much is downloaded and analyzed for, regularly? Okay, because this is one of the things that we discussed at the lab, is that when you install energy management system, you should also remember that there is a cost associated to it, which is to analyze the data. If you have the data, it is very, very, very powerful, because you know exactly what is the system level efficiency of your chiller. And you can identify later, 10 years from now, what is your chiller degradation, just by looking at your data 10 years ago. But obviously that is still considered expensive nowadays. But yes, we aim to download all the data from the energy management system. In many situations, this is the first time for many particular buildings, many buildings, not only this one. Our request is actually one of the first requests to download and trend the data. It's sad, because the data is there, and 1 terabyte hard disk right now is about $100. You can plug it in and you can download 1 terabyte of data, which will last quite long. 3 to 5 years of data. Just let it sit there until somebody pick it up and analyze the data, right? But maybe I'm different. I'm all for data, right? Maybe I'm different. But only if we don't have the data from the energy management system, then we go and actually log it, measure. Charlie.